Okay, so today we're going to review this idea of special right triangles. I think the last time you may have seen this would be in geometry, but we're going to review a couple key concepts with special right triangles. We're going to talk a little bit about what they are, because this is going to come in really handy as we start talking about trig and the unit circle. So if you kind of remember back from geometry, a right triangle is a triangle where you have one angle that is 90 degrees. It's where you have the perpendicular unison of a vertical and horizontal line makes 90 degrees, and it's going to look very similar to this, where that little box represents the 90 degrees. And you actually have two special right triangles when it comes to these types of triangles. And the first one is called your 45-45-90 triangle. And what that is these two angles are both 45 degrees, which means that these two sides are going to be the same length. So because your two interior other angles than the 90 degrees are both the same measurement, your two sides that form the 90 degrees are going to be the same length. So the general form for a 45-45-90 degree triangle, we're going to call these two sides x. And the proportion that's always going to hold true in a 45-45-90 is that if these two angles are both 45, these two side lengths are always going to be equal, and your hypotenuse is always going to be x times the square root of 2. So, for example, if I have a right triangle, we're going to call this triangle A, B, and C. And we're going to assume that this right triangle is a 45-45-90 to go along with this diagram. If we know that your side length AB is 12 centimeters long, then we can also assume that your side length BC is also going to be 12 centimeters long. And without having to do the Pythagorean theorem at all, you're going to be able to know, because it's a special right triangle, that your hypotenuse is going to be 12 square root of 2 centimeters long. Now you can take your calculator and take 12 times the square root of 2 and actually get a decimal value that would match what you would probably get if you were to do the Pythagorean theorem. But just for sake of using our special right triangle formulas, we're going to leave it as a radical form as your answer. So we're going to leave your answers just like that for right now. The other special right triangle that we're going to talk about is the 30-60-90 triangle. And a 30-60-90 is if you have one angle that's obviously your 90 degrees. Your other angle, your smallest angle, is going to be 30. So by default, your middle angle is going to be 60, because remember, in a triangle, all three angles have to add up to 180 degrees. In this special right triangle, you're also going to have a proportion that is always going to hold true. And that proportion goes like this. Opposite of your smallest angle measurement, which will always be 30, the leg opposite of that angle is always going to be considered x. Opposite of your 90 degrees, which is your longest side length, that proportion is going to be 2 times x. Which means 60, which is your middle angle, the leg opposite of 60 is always going to be x times the square root of 3. So that's going to be a proportion with your 30-60-90 right triangles that will always hold true. So one example that we're going to talk about real quick, we're going to call this triangle ABC again. If you're given an example like this, and we'll call angle A your 30 degrees, angle C will be your 60 degrees. If we're given right off the bat that side length BC is 35 inches, we can figure out the other two side lengths of that right triangle when we normally probably couldn't. One, we couldn't use Pythagorean theorem here because we only know one side. So to find out another side, or one of the other sides that we're missing, the proportion or relationship in a 30-60-90 triangle is that your smallest side length is x, which means your hypotenuse is always going to be 2 times that distance. So if BC, which is our smallest leg opposite of 30, is 35, we know that 2 times 35 is going to give us our hypotenuse, which we're going to get 70 inches for that length. Since x, which is your smallest side, is related to your largest side by 2 times that amount, 35 inches times 2 gives us 70 inches for our hypotenuse. To find our missing side length, which is opposite of 60, that proportion is always x times the square root of 3. So since x in this case is 35, we know that this side length, AB, is going to be 35 square root of 3 inches. Again, we can plug that into our calculator and get a decimal that we would be able to find if we use Pythagorean theorem at this point, but we're going to leave it as in radical form. Okay, so we're going to go through a couple extended videos together before you guys work on numbers 1 through 10 on your own for our next class meeting. So in part 1, we're going to assume that this is going to be 45, 45, 90, special right triangle. And let's say that I tell you right off the bat that your hypotenuse is 5 square root of 2. Let's say that's the only piece of information that you know, that this is a 45, 45, 90 right triangle and that your hypotenuse is 5 square root of 2, we'll call it inches, we'll do inches long. So from that information, can we find the other 2 missing side lengths? We'll call it A, B, and C. So we want to find what the length AB is and what the length BC is. So according to our diagram on the same sheet of paper, we know that 45, 45, 90 triangles have a certain proportion that will always hold true. So in this case, since my hypotenuse is 5 square root of 2 inches, just like up here in my diagram, the x value that's out in front, which in this case happens to be 5, is also going to be the side lengths of my 2 legs, which is leg AB and BC. So given this information only, I know that AB is going to be 5 inches, and I also know that BC is going to be 5 inches. Let's look at another extended example. We'll call this triangle XYZ. And let's say this is going to now be a 30, 60, 90 right triangle. And let's say the only information we're given here is that YZ, this leg, is 4 centimeters long. So normally we wouldn't be able to use Pythagorean theorem here because we have 2 missing side lengths, and for the Pythagorean theorem to hold true, or for us to be able to use it, we have to know at least 2 of them. So in this case, if I only know the leg YZ is 4 centimeters, because this is the smallest leg, because it's opposite of my smallest angle, I know that my other leg, that relationship, is going to be x times the square root of 3. It's going to have the same relationship as 4 with the square root of 3 right after it. So the relationship between these 2 legs is if this one's 4, then this one's going to be 4 square root of 3. That's going to be the middle leg, the middle longest side, because it's opposite of your middle biggest angle, which is 60. You can also find that your hypotenuse is going to be twice the size of your smallest side, which is 4. So 4 times 2 gives you the hypotenuse of 8 centimeters. Last but not least, we're going to look at one more extended example, and we're going to call this triangle JKL. And let's say that this is also a 30, 60, 90 triangle, special triangle. And let's say, for example, we know that our side length opposite of 60, so our middle, or our second biggest side length here, is going to be 10 square root of 3. from there, can we find the missing side lengths of KL and JL? And in fact, we can. If we know that opposite of 60 is the side length 10 square root of 3, we take that x value that's out in front, which is 10, and we know that that's going to be the smallest side length that we have. We also know that our smallest side length is related to our hypotenuse, or our largest side length, by 2 times that amount. So 2 times 10 gives us 20. So those are how those 3 side lengths are related in the special right triangles. So from here on out, you have 10 problems that's part of this Blackboard Assignment 4 that you can work on your own, and we'll go over those answers together at our next class meeting.